In the application of equilibrium to beams, there are several things to keep in mind right off the bat. One of them is that you usually have to find the reactions right away. So that's what you see here is a review of how to calculate those reactions. It turns out that the reaction at B is equal to 25 kips acting up, and the reaction at A is equal to 21 kips also acting up. Right, so that's number one. Typically you need to find those. Now, not always, because it is the case, such as in the overhang, that if you want to find the shear moment at a point inside the beam, that you could simply cut that beam, in this case, an overhanging free piece, and you would then expose those internal forces at that cut point. You'd have the internal beam shear, you'd have the internal bending moment, and an axial force at present, which is not in this case. And from equilibrium alone of that, you could find those internal values, right? But otherwise you do have to find the reactions first. And it brings up the second point, which is why exactly would you choose, or what direction do you choose to show these internal bending moments and shears? And there it comes back to, from a bending perspective, that in the American Designer Sign Convention, that a positive bending moment tends to create a smiley face deflected shape, as opposed to then the shear forces look like so, upwards on the left, downwards on the right, and I don't have any nice, pretty, fancy way to remember exactly what that is. And instead, actually, what I do is I remember how to draw shear moment diagrams to then reverse engineer what the appropriate sign convention is. And when you're doing shear moment diagrams, the key there is that the rate of change of the shear is equal to the load intensity, and that the rate of change of the moment is equal to the intensity of the shear at that point. Because typically what we do in real structural applications is not to find the shear and bending moment at a point, but rather instead what we're going to do is find the shear and bending moment everywhere. So much fun that we want to find it everywhere we possibly can. Well, no, actually we're looking for the maximum values for design purposes, and so that means indeed doing it everywhere. And remember that when we're doing the shear diagram, that we're going to start off at 0 at the left, and then we're going to follow the point loads and the distributed loads and how they impact things. So a discrete load creates a discontinuity in the shear diagram, and we just follow the direction of that. So an upwards load creates an upwards discontinuity, so we go from 0 to 21. Distributed load is not just the magnitude of the load intensity, it actually tells us exactly what the slope of the shear diagram is. A -2 kip per foot means that we have on the slope, or excuse me, on the shear diagram, a negative slope of 2 kips per foot. It actually tells us that for every foot I go, I change and decrease the shear by 2 kips. Right? And if we do that over 20 feet, then we'll go start at 21 minus a total of 40 to get to a value of negative 19 in over at the other reaction. Right? And so that will be a slope that's constant, and that will turn into a first order curve, or straight line if you will, that ends up being at minus 19 on the other side. Then we get another discrete load, a instantaneous change, so we go from minus 19 plus 25 to a net of 6, and then we close that off when we get over to the end where we have that downwards force of 6, and close off as we would hope that it would. That doesn't tell us that we've done all the math right. When we go do the moment diagram, if it also closes off properly, then we'll be in pretty darn good shape. I'll have a lot of confidence that we've done this math correctly. Right? And so now we come back and we set up our axis for the moment diagram. Note that it will now have units of foot kips, and that at the end of the beam we have a frowny face moment of 56 kip foot. That's negative in our sign convention, so we're going to start off by having an instantaneous jump down from 0 to minus 56. And then we note that, gee, we've got a value of the shear at some point that is equal to 0, and that tells us that we have 0 slope on the moment diagram. That location by similar triangles is going to be at 10.5 from the left, 9.5 to the right. I don't have to just do similar triangles to do that. Note, once again, we start off with a shear of 21 positive, and we have a negative 2 kip per foot change in the shear as we go along. So to get 21 at a down to 0 at a decreasing or at a constantly decreasing rate of 2 kip per foot is going to require 10.5 feet. In that area, that total change in the moment then is going to be given to us by the area of that triangle, and that's 110.25, 1/2 the base times the height, and that's going to leave us with a net here from minus 56 plus 110.25, a net of 54.25. Right, now I'm not going to draw the curve in just yet because I want to go find out then what the area is of this other triangle, and that will be an area of 90.25, but because it's below the axis we call that a negative area. It's a negative change in the moment, right? And so 54.25 minus the 90.25 will get us to a minus 36 over here at support point B. And now I pull out the French curve. I don't need to do this perfectly to scale. I'm just trying to get this reasonably appropriate. You got 3 points. That helps me to draw the curve. And now there's our second order curve. It's not terrific. We got probably just a little bit too much slope over here at the right hand side, but it gets us in the right ballpark. And then notice that we've got to take care of the overhanging part. That area there is 6 times 6 or 36 because it's 6 foot long, and note that it has a constant slope, so therefore we're going to go up from minus 36 plus 36 gives us right to 0. That's good. It should close off and straight line, and there's your moment diagram. So note we've got a region of positive moment, that's the smiley face part. We got region of frowny face moment, that's the negative